Welcome to MrCScience.com's video on energy, heat, and temperature. We're moving into the science of heat and temperature here in chemistry. Let's define a few terms first. Let's start with energy. Energy is the ability to do work, or energy is required to do work. Well, that begs the question, what is work? Work in physics is designed or is described as force times distance. Or another way of doing that is work is taking an object and moving it a distance by applying a force to it. The amount of force required times the amount of distance the object is moved is called work. Now this idea of energy works pretty well if you think of just the world itself and pushing a cart around or picking up things, moving things. All that requires work to do. But we got another thing we're working with here is heat. Heat is energy transferred from high heat to low heat. So heat is energy. Energy is the ability to do work. And work is a force that allows us to move a certain distance. Well, heat isn't as obvious characteristics of doing work, but it can. If we look at, say, you boil water, you apply heat to that water. Now, the work being done isn't that obvious. I mean, obviously, if you boil it, you see the bubbles moving, the gas rising, that's work. Well, the heat or the work being done there is movement of the molecules within the water. We know as we increase the heat on an object, it moves more. So that's the heat. Take another thing, say burn a log on a fire. If you do that, you get heat out of that log, quite a bit actually, enough to warm a large area for a long amount of time. The question is though, where does that heat come from? Where does that energy come from? Because you pick up the log by itself, it's not warm already. We're not seeing energy transferred from high heat to low heat. We're actually seeing the creation of heat. So where does that come from? That brings us to laws of thermodynamics. Specifically the first law of thermodynamics. If you look at the name thermal, heat, dynamic, movement. Thermodynamics, movement of heat. First law of thermodynamics says energy cannot be created or destroyed. It can only change forms. So the energy that we get when we burn a log wasn't actually created. It was already inherent in the log itself, and it was released. It changed forms. It went from one type of energy to another type of energy. We call these two types of energy potential energy and kinetic energy. The energy you're probably most familiar with is kinetic energy. That's the actual energy released. So when we burn the log, that's the energy that's created that we see in the form of heat and light coming off. That is kinetic energy. Potential energy is energy that is stored, that can be released. So in the log itself are molecules of cellulose, water, a bunch of other things in there that are all tied up. When we burn it, we break some of these bonds and we release the energy from those bonds in the form of heat. So that's potential energy. First of all, kinetic energy, which we're familiar with. Kinetic means movement in science, so energy in motion. That's energy moving in the form of heat, moving from an area of high heat to low heat. Potential energy is stored energy, so there is a potential there. The log has only so much energy that can be released on the campfire. Eventually it burns up, releases everything into the form of carbon dioxide, water vapor, carbon, and other trace elements of other things left in there, but it will no longer burn on the fire. You need to put another log on the fire. That is potential energy. Each log has a potential of releasing a certain amount of kinetic energy or stored energy. So let's talk about units of energy. So we like to track how much energy is released or stored in an item. The first unit we're going to talk about, and the one will probably be used the most, especially if you go into college chemistry, is the joule or joules, denoted by a capital J. Joules are a measure of energy that we most commonly use. A joule is a measurement of force over distance, or force is newtons, distance is meters, so a joule is a newton meter, named after a famous scientist that discovered this. So let's talk about a different way of measuring energy. A calorie, denoted with lowercase c. A calorie is the amount of energy required to increase 1 gram of water or 1 milliliter of water 1 degree Celsius. So calories are another way of applying that. 1 calorie equals 4.184 joules, or thereabouts, depending on your significant figures. Another thing that's probably more familiar, the word calorie sounds familiar to you, but really what they're talking about is a dietary calorie, denoted with a capital C. 1 dietary calorie equals 1,000 calories, or 1 kilocalorie. So dietary calories, because there's so much energy in food, to talk about calories, we'd have to actually talk about thousands of calories instead of single calories, so or 1 kilocalorie. So your standard, average standard recommended caloric intake in dietary calories is 2,000 calories, which would be 2 million lowercase c calories, so or enough energy to take 1 gram of water and raise it 2 million degrees Celsius. So a lot of energy stored in food, a lot of potential energy there. Okay, so let's talk about measuring this heat. So there's a formula you're going to need to know. I'm going to write it out here. Q equals MC delta, that's a triangle, T. Q equals MC delta T. Q is energy, usually in the form of joules, but we can also use calories here. M, you should be familiar with, lowercase m is mass. Delta T, we'll skip the C for a second. Delta T is change in temp. And you may remember that delta T is going to be, delta T is going to be equal to our temp final minus our temp initial. So whatever our final temp was minus our initial temp will be our delta T. C is a new term called specific heat. Specific heat, you can see how it's defined here. If we ignore our calories and use joules instead, then our C equals Q over M delta T, or joules per kilogram degrees Celsius. Oh, sorry, they don't use kilograms. That's my mistake. I thought that seemed a little weird. Jumping back to physics. Joules per gram Celsius. So this is a quantification of the amount of energy it takes to raise 1 gram of a substance 1 degree Celsius. How many joules does that take? So let's go through some basic ones. So in your book, you'll see a list of specific heats for common substances. On the tests, you will not need to know that. They will give you all the specific heats you need. So they give some, let's pick a couple obvious ones here. Let's start with water. Water. Its specific heat is 4.184. 84 joules per gram Celsius. That number may look familiar. If we go back up here, 1 calorie equals 4.184 joules. So specific heat is 4.184 joules per gram Celsius. If we take something different, let's start with, let's grab copper. Copper, that's supposed to be a U. A second. There, that looks better. C equals 0.3851. 0.3851 joules per gram Celsius. Now you may notice a big difference between these two numbers. Water has a very large number. It takes a lot of energy to raise the temperature of water. Copper conducts energy very well. It takes very little energy to raise the temperature of copper. We can see that it's at least 10 times easier, a little more than 10 times easier to raise the temperature of copper than it is for the temperature of water. So if we applied, let's do this. So if we took our energy and energy of, let's say, water, and if we used our Q equals mc delta T, then if we took mass of 1 gram of water, our C is 4.184 joules per gram Celsius. And if we want to raise that, say, 10 degrees, so we want to do a delta T of 10 degrees Celsius. If we multiply all that out, we get that Q of water will be equal to 41.84 joules of energy required. If we do the same thing for copper, let's give ourselves a little more room here. So if we take our Q copper and we do a mass of 1 gram and times its C of 0.3851, and we also want to raise it 10 degrees Celsius, so we want to change its temps by 10 degrees Celsius, then we're going to get 3.851 joules required. So you can see a very different amount of energy, all based on the specific heat. How hard is it to transfer heat into or out of the substance? That's one of the reasons it takes our lakes so long to freeze during the winter, because it takes a lot of energy or it takes the release of a lot of energy to get them to go down. And then to thaw them in the spring, they take a while because it takes a lot of energy pumped into them to raise their temperature up to hit thaw point. Okay, I think I'm going to do the calorimeter in another video here. So things to get out of this is your definitions, and then also know your formula. Q equals mc delta T. This we're going to use in the next video for calculating heats in a calorimeter. We'll talk about that. If you have any questions or questions, drop me a line at mrc@mrcscience.com. Thank you.